Evaporator. The evaporator, like the condenser, consists of a refrigerant coil, mounted in a series of thin cooling fins. It provides a maximum amount of heat transfer, in a minimum amount of space. The evaporator is usually located beneath the dashboard, or instrument panel. Upon receiving the low-pressure, low-temperature liquid refrigerant from the thermostatic expansion valve, or orifice tube in the form of an atomized, or droplet spray, the evaporator serves as a boiler, or vaporizer. This regulated flow of refrigerant boils immediately. Heat from the core surface is lost to the boiling and vaporizing refrigerant, which is cooler than the core, thereby cooling the core. The air passing over the evaporator loses its heat to the cooler surface of the core, thereby cooling the air inside the car. As the process of heat loss from air to the evaporator core surface is taking place, any moisture or humidity in the air condenses on the outside of the evaporator core and is drained off as water. A drain tube in the bottom of the evaporator housing leads the water outside the vehicle. This humidification of air is an added feature of the air conditioning system that adds to passenger comfort. It can also be used as a means of controlling fogging of the vehicle window. Under certain conditions, however, too much moisture can accumulate on the evaporator coils. An example would be when humidity is extremely high and the maximum cooling mode is selected. The evaporator temperature might become so low that moisture would freeze on the evaporator coils before it could drain off. Through the metering or controlling action of the thermostatic expansion valve or orifice tube, greater or lesser amounts of refrigerant are provided in the evaporator to adequately cool the car under all heat load conditions. If too much refrigerant is allowed to enter, the evaporator floods. This results in poor cooling due to the high pressure and temperature of the refrigerant. The refrigerant can neither boil away rapidly nor vaporize. On the other hand, if too little refrigerant is metered, the evaporator starves. Poor cooling again results because the refrigerant boils away or vaporizes too quickly before passing through the evaporator. The temperature of the refrigerant vapor at the evaporator outlet will be approximately -15 to -8.8 degrees Celsius higher than the temperature of the liquid refrigerant at the evaporator inlet. This temperature differential is the superheat that ensures that the vapor will not contain any droplets of liquid refrigerant that would be harmful to the compressor. Refrigerant lines. All the major components of the system have inlet and outlet connections that accommodate either flare of O-ring fittings. The refrigerant lines that connect between these units are made up of an appropriate length of hose or tubing with flare or O-ring fittings at each end, as required. In either case, the hose or tube end of the fitting is constructed with sealing beads to accommodate a hose or tube clamp connection. There are three major refrigerant lines: suction, liquid, and discharge. Suction lines are located between the outlet side of the evaporator and the inlet side, or suction side of the compressor. They carry the low-pressure, low-temperature refrigerant vapor to the compressor, where it is again recycled through the system. Suction lines are always distinguished from the discharge lines by touch and size. They are cold to the touch. The suction line is larger in diameter than a liquid line, because refrigerant in a vapor state takes up more room than refrigerant in a liquid state. Beginning at the discharge outlet on the compressor, the discharge, or high-pressure line connects the compressor to the condenser. The liquid lines connect the condenser to the receiver, or dryer, and to the inlet side of the expansion valve. Through these lines, the refrigerant travels in its path from a gas state, from compressor outlet to a liquid state, at condenser outlet, and then to the inlet side of the expansion valve, where it vaporizes on entry to the evaporator. discharge, and liquid lines are always very warm to the touch, and easily distinguishable from the suction lines. Aluminium tubing is commonly used to connect air conditioning components, where flexibility is not required. Where the line is subjected to vibrations, special rubber hoses are used. Typically, the compressor outlet and inlet lines are rubber hoses with aluminium ends and fittings. R134A systems are required to be fitted with quick disconnect fittings throughout the system. These systems also have hoses specially made for R134A. They have an additional layer of rubber that serves as a barrier to prevent the refrigerant from escaping through the pores of the hose. Some late model 12 systems also use these barrier hoses to prevent the loss of refrigerant through the walls of the hoses. Sight glass. The sight glass allows the user to see the flow of refrigerant in the lines. A sight glass is normally found on system using R12 and a thermal expansion valve. It is not commonly found on R134A systems. It can be located on the receiver or dryer, or in line between the receiver or dryer and the expansion valve or tube. To check the refrigerant, open the windows and doors, set the controls for maximum cooling, and set the blower on its highest speed. Let the system run for about 5 minutes. Be sure the vehicle is in a well-ventilated area, or connect an exhaust gas ventilation system. Use care to check the sight glass while the engine is running. If oil streaking is seen, this indicates the system is empty. Bubbles, or foam, indicate the refrigerant is low. A sufficient level of refrigerant is indicated by what looks like a flow of clear water, with no bubbles. A clouded sight glass is an indication of desiccant contamination, with subsequent infiltration and circulation through the system. Accumulator systems do not have a receiver or dryer to separate the gas from the liquid, as it flows from the condenser. The liquid line will always have a certain amount of bubbles in it. Therefore, it would be useless to have a sight glass in these systems. Pressure and performance testing are the only ways to identify low refrigerant levels.